Skyberg. No, sorry, I'll start again. My name is Matthew Skyberg, and for my capstone project, I chose to do street tree equity and understanding the socioeconomic and zoning factors of street tree distribution in the city of Los Angeles, California. The city's urban forestry department. Oh, one sec. Okay. Okay, city's urban forestry division manages nearly 700,000 street trees. And this makes it the largest urban forest in the nation and possibly the world. And it's also the most diverse urban forest in the world. There are many benefits of urban tree canopy and specifically street trees. And many of the environmental benefits correspond to health benefits, such as trees remove air pollutants and produce oxygen, thus improving air quality. Through shading and evapotranspiration, trees decrease surface temperature, reducing the heat island effect and lowering risk for heat-related health issues. And trees also reduce the impacts of stormwater runoff and, of course, provide habitat for urban wildlife. Foliage also helps reduce noise pollution and light pollution from vehicles, which is especially true with street trees along traffic corridors. And there are also economic benefits such as increased property values and lower utility costs, such as less air conditioning needed because of tree shading. So all these benefits should be enjoyed equally by all residents of the city. And street trees are unique because they occur in the public right-of-way. So other than public parks, street trees are some of the only publicly accessible trees in cities. Unfortunately, past studies have shown that this distribution is typically not equitable and for a variety of factors. So past studies have shown socioeconomic factors that correspond to lower urban tree canopy coverage include lower income levels and higher poverty rates, higher percentage of racial or ethnic minority population, and lower levels of education attainment. And there are also other constraining factors that prohibit street tree planting. In Los Angeles, new street trees require 3 to 5 years of establishment period, where watering and maintenance is the responsibility of the property owner. And automatic irrigation is not typically feasible because it requires a special permit, which increase timeline and cost on construction projects. And it's not really a means for retrofitting because it requires removing sidewalk paving. There are also infrastructure constraints as some public right-of-ways don't have adequate space for new street trees. There's competition with driveways, street lights, street signs, electrical poles, fire hydrants, utility meters, etc. So it's hard to always find a space for a street tree. And also past policies such as redlining and current land use and zoning policies have contributed to the distribution we have today. Los Angeles has embarked on 2 ambitious tree planting campaigns under the 2 previous mayors. In 2006, the Million Trees LA initiative was started under Mayor Villaraigosa. They hope to plant 1 million trees by 2010, which wasn't realized, but they did end up planting over 400,000 new trees in his term. Then in 2019, LA's Green New Deal was started by Mayor Garcetti, and they had a goal of 90,000 new trees by 2021, which unfortunately was not met as they stood at just over 65,000 trees installed as of June of 2022. And they're still working on getting up to that 90,000 number. They also had a goal to increase urban tree canopy by 50% by 2028 in the areas with greatest need. However, the Green New Deal didn't really specify what these areas were or what the criteria was for the areas of greatest need. And so with my project, I'm hoping I can help locate some of these areas. So I believe a spatial relationship does exist between street tree distribution and socioeconomic, historic redlining, and zoning factors in the city of Los Angeles. My study area consisted of the city of Los Angeles, which is located in Southern California on the Pacific coast. And the city includes diverse landforms such as mountains, valleys, and basins. And it's very irregularly shaped, as you can see in the map, and interrupted by other cities in the metro area. Los Angeles is the largest city in California with nearly 4 million residents who enjoy a moderate Mediterranean climate. So I first obtained the data necessary in order to perform this analysis, and then use the data to create a street tree index and perform regression analysis, which was able to produce an OLS model without a high level of certainty, but it did identify significant variables. So the data used included the 2020 US Census data at the census block group level, the homeowners loan corporation boundaries, redlining boundaries from the 1939 map, city zoning boundaries, including land use and hillside areas, National Agricultural Imagery Program rasters to cover the entirety of the city from the 2020 growing season, and city data including streets and street trees. So the relevant 2020 census data was added at the census block group level for the entirety of the city of Los Angeles. The census data was included to calculate the following socioeconomic factors. I won't go through all of them, but they include population density, race and ethnicity, vulnerable age groups, means of transportation, education attainment, household language, poverty levels, unemployment, amongst others. Here's the redlining boundaries from the 1939 map, which is provided in a digital format from the University of Richmond's Digital Scholarship Lab. These were created at the county levels for Los Angeles, and the boundaries didn't conform to the census block group boundaries. I also obtained the land use zoning boundaries from the city of Los Angeles, which includes 7 classifications of land use, with residential, shown in yellow on the map, being the most prominent throughout the city. And the hillside ordinance boundary was also obtained from the city of Los Angeles. And these areas are hillside areas that have special requirements for development. The NAPE imagery was from the 2020 growing season. And this included 60 rasters to cover the entirety of the city. All images were taken between April 25th and May 21st of 2020. The city's streets polylines, as shown by their center lines, was obtained from the city of Los Angeles, GeoHub, as well as the city's street trees shown as points. So using this data, I calculated socioeconomic and zoning factors at the census block group level and calculated a street tree index in order to perform the regression analysis. The 2020 census block groups were projected into the state plane coordinate system for Los Angeles, and relevant data was joined to calculate the socioeconomic variables. The study area was defined by excluding census block groups that were less than 50% in the city limits, and those that had a population density of less than 250 people per square mile, and census block groups with a null value for housing vacancy. The study area census block groups are shown in light green, and the excluded areas of the city are shown in darker gray on this map. Then I used the summarize within tool to determine the area of each redline classification and each census block group, and calculated the percent for each classification for all the census block groups. So in this map, we can see that the values range from 0 to 100% for each redlining classification. I used a similar workflow for the land use zoning and the hillside zoning to calculate the percentage of area for each zoning classification and each census block group. The street tree index used a normalized difference vegetation index to determine the vigor or lushness of street tree canopies, which provided a qualitative factor for the street tree index. So these NDVI values were extracted from the street tree points or to the street tree points, which were then used along with the calculated street frontage to produce the street tree index. The NAPE rasters were used to create a mosaic data set to cover the extent of the study area. Then the NDVI was calculated using the formula near infrared band minus red band divided by the near infrared band plus red band, which are band 4 and band 1 in the NAPE imagery. These values were then extracted to the street tree points as shown in this map. The city streets were buffered by 25 feet to create a typical street frontage. And then the summarize within tool was used to calculate the total length of street frontage per census block group. And then the summarize within tool was also used to summarize the number of street trees per census block group and the average street tree NDVI value per census block group. And then those were used to calculate the tree index, which was the number of street trees divided by the total length of street frontage times the average street tree NDVI value per census plot group. And that's shown in this map here, where we can see higher concentrations of the tree index score in the central portion, as well as some of the east San Fernando Valley and spots throughout the west side. The calculated tree index was then used as the dependent variable for regression analysis, along with a total of 37 socioeconomic and zoning independent variables. ArcGIS Pro spatial relationship tools were used in regression analysis. So exploratory regression uses ordinary least squares regression on all combinations of the independent variables specified and performs tests to determine the best performing model. Through this, exploratory regression identified 4 best performing models that scored nearly equal on the fitness test. And the model with 18 variables that had a AICC more than 3 points lower than the next best performing model was chosen for ordinary least squares regression. So ordinary least squares produces a global model with a single equation to explain the explanatory variable across the study area. And it delivers diagnostic information that informs us of the performance and fitness of the model and coefficients that inform the relationship between the explanatory variables and the dependent tree index variable. The model produced by OLS overpredicted many areas in the Santa Monica Mountains and in the north and east foothills of the San Fernando Valley. It also underpredicted in the central portion of the study area, as we can see here, and the overprediction occurring in the mountains and pockets of the foothills of the San Fernando Valley. So with the standard residuals, we can see the areas in dark red where the model is overpredicting. Primarily, we can see a couple clusters that occur in the foothill areas. And areas in dark blue are where the model is underpredicting. And that's mostly in the central portion and eastern San Fernando Valley. The areas in light yellow are where the model is performing best. By looking just at the residual values, we can see these areas kind of further pronounced where they're happening. So the OLS diagnostics show that 2,652 census block groups were included in the study area. The AICC was the best performing of the models tested in exploratory regression. And the adjusted R squared was just over 0.28, which means that the model is only explaining about 28% of the variation in tree index values. The Conquer statistic was statistically significant. That indicates heteroscedasticity. So the model is not linear, and this might mean that it's a candidate for geographically weighted regression. The Harkibera also was statistically significant, and so the module residuals are not normally distributed, and the model is biased or not trustworthy. This bias is likely due to missing key variables. Analyzing the spatial autocorrelation with Moran's I tool, we can see that the residuals were far beyond the acceptable Z-score, and they're significantly clustered. And this confirms that a key variable is missing, causing this misspecification. So the OLS summary shows us that the BIF was well below 7.5 for all the model variables, and there's no significant redundancy among variables, and all variables were statistically significant. Geographically weighted regression was attempted, but I was unable to use the same key variables as the OLS model due to multicollinearity. And so the GWR model was not able to perform as well as the OLS model. So despite not being able to identify properly fitted regression models, some key explanatory variables were identified. Positive relationship indicates high index value when the explanatory value also increases. So all the red line areas had a positive relationship, although the areas classified D were less positive than the other 3. And Asian Pacific Islander household language, associate or bachelor's degree education attainment, and commuting by public transportation or walking were also positive, as well as senior population age 65 plus. Some of the visual relationships you can see, the areas that are red line D do correspond to a lower tree index in the eastern portion of LA. Asian or Pacific Islander household language also correspond in the central portion where there's a higher concentration, but less so in the San Fernando Valley areas where there's a lower index value with a higher percentage of Asian or Pacific Islander household language speakers. The negative relationships, all the zoning areas other than residential did have a negative relationship with the tree index, but the other ones were Black or African American populations were strongly negative, and populations at or below the poverty line. So we can see the hillside areas, it's very clearly there is a correlation with tree index, although less so in the eastern portion. And then the Black or African American population is mostly concentrated in the central and southern portion of the study area, which also corresponded to lower tree index values. As same with the population at or below poverty line, that corresponded in the eastern and south central portions, but not as much in the San Fernando Valley. So the results of this study help target some of the populations that are negative related to the tree index, and this could be used to help target these groups with means specific to them to try and increase this tree index. And policymakers could also provide incentives, particular land use zoning areas, or provide city installed and maintained trees to areas of most need instead of relying on individual property owners. So conclusions, urban tree canopy and street trees are essential to the city's health and well-being, and street tree distribution is not equitable in Los Angeles for a variety of reasons. However, additional variables are needed to better understand the explanation or explain the street tree distribution in the city of Los Angeles. However, the city can now prioritize cities with lowest street tree index, along with other variables, and try to tackle the areas most affected by environmental health issues and improve street tree equity in the city of Los Angeles. And with that, I'll open up to any questions you might have.